Here the question is, which of the following ionic species will impart color to an aqueous solution? Here, color of the substance depends on the d configuration and unpaired electrons. Ions with d1 to d9 configuration will be colored because with d1 to d9 configuration they have unpaired electrons in them which are responsible for dd transition and color. Here we have to find out the d configuration of these given ions. D configuration can be obtained by taking valence electrons of the atom minus the charge on the ion. We get D configuration. For example, titanium 4 plus. It has valence electrons 4 and it has lost all the 4 electrons because the charge here is 4 and it is left with D0 configuration, no unpaired electrons here. Cu plus ion, copper has valence electrons 11 where its charge is plus 1, lost 1 electron, and it shows D10 configuration where again no unpaired electrons. The third option, Zn2 plus, has valence electrons 12. Its charge is 2, lost 2 electrons, end up with the D10 configuration again with no unpaired electrons. The last option, chromium 3 plus, has valence electrons 6 and the charge is 3. It has lost 3 electrons with D3 configuration. Here it shows 3 unpaired electrons which are responsible for dd transition and the color of the ion. Therefore, our answer should be D option here. The question is like that, which of the following ions is most stable in aqueous solution? We are given with the ions here. In aqueous solution, the stability of the ion is governed by crystal field stabilization energy. Stability of ion depends on crystal field splitting energy and electronic configuration, by which we get D configuration. We come to know D configuration and that helps to predict the stability of the ion here. Now let's take the first option, chromium ion here. Chromium, when surrounded by water molecules which are acting as a ligand here, water molecules acting up as ligands here, the degenerate d orbitals in chromium will split into lower energy and higher energy orbitals here. Based on the electronic arrangement in these orbitals, the stability of the ion can be predicted. In Cr3+, which has 6 valence electrons, by losing 3 electrons, it will end up with D3 configuration where the lower orbitals will be completely filled here and that gains stability for the ion. Whereas when we observe V3+, vanadium has 5 valence electron and it has lost 3 electrons with the D2 configuration, meaning the lower orbitals will be filled with only 2 electrons and 1 remains vacant here, like this for vanadium 3 plus ion. Whereas when we talk about titanium 3 plus, titanium has 4 valence electron, it has lost 3 electrons and it ends up with D1 configuration where it will have 1 unpaired electron in its lower energetic orbital Ti3 plus. When we speak about manganese Mn3 plus, the valence electrons of manganese is 7, lost 3 electrons, end up with D4 configuration where manganese ion will have 4 electrons in its lower shell and 1 in the upper. And here it tends to lose one electron. Manganese tends to lose one electron and get reduced to Mn2 plus. So it is unstable in aqueous medium. Even titanium, it tends to get oxidized to Ti4 plus, where it will end up with 3D0 configuration. Manganese with the 3D5 configuration here, I mean to say 3D3 configuration here, and even vanadium is also unstable here. It tends to jump from D2 configuration to D0 configuration. So these ions remains unstable, whereas chromium remains stable because of its 3 unpaired electrons in the lower energetic orbitals. Therefore, our answer should be A option, which is most stable. When we look at the question, among the following series of transition metal ions, the one in which all metal ions have 3D2 configuration. Which one has 3D2 configuration? We have to find out here. See, D configuration can be obtained by taking valence electrons minus charge on the ion. We get D configuration. Let's find out that which ions among these will have D2 configuration. The atoms given here are titanium, vanadium, chromium and manganese. The valence electrons of titanium is 4, and how many electrons it has to lose in order to get 2 electrons, that is D2 configuration. It has to lose 2 electrons. Therefore, titanium should exist in 2 plus state. The same way, vanadium valence electrons are 5. In order to get D2 configuration, it has to lose 3 electrons here. So, vanadium should exist in 3 plus state. Chromium valence electrons are 6. In order to get D2 configuration, it has to lose 4 electrons, meaning chromium should be in 4 plus state. Manganese valence electrons are 7. In order to get D2 configuration, it has to lose 5 electrons. So, manganese should exist in 5 plus state. When we look at the option, the B option has titanium 2 plus, vanadium 3 plus, chromium 4 plus and manganese 5 plus. Therefore, option B should be our answer. The question is like this. The correct order of the ionic radii of yttrium 3 plus, lanthanum 3 plus, europium 3 plus and lutetium 3 plus atomic numbers are given. We have to find out the correct order here. The ionic radii of the ions, depends on the charge. It depends on charge of the ion. And it depends upon the position of the atom. In periodic table. As here the charges are all 3 plus given here, then we have to focus on the position of the atom in periodic table. When we look at these ions, lanthanum, europium, lutetium, all these are F block elements, 4F series elements which are arranged this way. In lanthanoids across the series, the atomic size decreases. Therefore, from this we understand lutetium 3 plus ion will have lesser size when you compare with that of europium and then lanthanum trivalent ions this way. When we talk about yttrium is placed just above the lanthanum. It is seen in 4D series of D block. Lanthanum is seen in 5D series here. When we come from top to bottom in the group, the atomic size increases. Therefore, yttrium size should be smaller than lanthanum. It is found that yttrium trivalent ion has size smaller than europium and greater than lutetium, meaning it comes somewhere here. Yttrium size comes somewhere here where the size is smaller than lutetium, it has size smaller than europium and greater than lutetium. When we look at the option, C option fits correct here where lutetium 3 plus will have smaller than yttrium, europium and lanthanum. So our answer should be C option. The question is like this: which of the following pairs have same size? The size of ions depends on their charge carried by them and the position of that atom in periodic table. Now let's talk about the size of these ions here given. When we observe these ions, they all belong to D block like 3D, 4D and 5D series elements. When we look at these 3D, 4D, 5D series elements, titanium is seen in 4th group, whereas iron is seen in 8th group, nickel is seen in 10th group of 3D series. Zirconium is seen in 4th group just below titanium and hafnium below zirconium in 4th group. We know in 3D series, across the series, the atomic size decreases. Therefore, these three elements cannot have same size. When we bother about down the group, the atomic size has to increase. But here, zirconium and hafnium both will have almost same size this way. They both will have same size, where zirconium will show 160 picometer, whereas hafnium will show 159 picometer. Same size are seen. That is due to lanthanoid contraction experienced by 5D series elements. Lanthanoid contraction is due to poor shielding of 4f electrons. 4f electrons poorly shield the outer electrons. Therefore, these elements show contraction called as lanthanoid contraction that makes zirconium and hafnium to have almost same size. So, our answer should be D option, where zirconium and hafnium both are in 4 plus state here. The question is, which ion has maximum magnetic moment? Magnetic moment is directly proportional to number of unpaired electrons, d electrons. Magnetic moment increases as unpaired electrons increases. Unpaired electrons can be found out by deconfiguration. Deconfiguration can be found out by taking valence electrons minus charge on the ion. Let's find out here. Vanadium is 3 plus, manganese is 3 plus here, whereas iron is also 3 plus. Copper is in 2 plus state. The valence electrons of vanadium is 5 minus 3. It ends with D2 configuration with 2 unpaired electrons here, whereas manganese 7 valence electron lost 3 electrons because the charge is 3, and it ends with D4 configuration, meaning there are 4 unpaired electrons. Iron has 8 valence electron lost 3 electrons, ends with D5 configuration, meaning it has 5 unpaired electrons here, whereas copper has 11 electrons lost 2 electrons. It will have D9 configuration, meaning 1 unpaired electron. When you look at the table, iron has 5 unpaired electrons, therefore its magnetic moment should be very high. So our answer should be C option, because here vanadium has 2, manganese has 4, copper has 1 unpaired electron. The question is, which is not amphoteric? When we observe the ions like aluminium, chromium and zinc ions, it is observed when these ions react with bases, they produce their respective hydroxides. Whereas when they react with an acid, these ions will produce their respective salts like aluminate, chromite and zincate salts. Whereas Fe3 plus ion, when dissolved in water, immediately Fe3 plus coordinates with the OH of water, coordinates tightly with the OH of the water and loosens the bond between OH and H. H get deprotonated easily as H plus ions and makes it highly acidic. So FeOH thrice is highly acidic in nature and weakly basic here. As it is weakly basic, it cannot react with another acid as it is highly acidic. So in our options, Fe3 plus is not amphoteric, the rest all are amphoteric in nature.